Swayam Prabha. Digital India. Educated India.
So now for today's class we'll start with a new topic on microcontroller architecture, and in that we'll particularly look from the perspective of interfacing sensors and actuators, and different kinds of microcontroller that we will need to know so that we can choose appropriate ones for the application that we are looking for. Okay, so I'm presuming for this class that you already have some exposure to the microcontroller programming and some kind of idea about how things go, and we'll build on those ideas now to kind of get to more advanced versions of microcontrollers. And one of them is TIVA board, which is ARM Cortex M4 series microcontroller board that we will take up for programming in this class. Okay, and we'll build some of the experimental understanding based on that syntax. Okay, so now for a couple of classes, we'll look at this microcontrollers, its programming details, some of the details, and I'll post a lot of material for that, and you will get to kind of understand. Once your microcontroller boards are there with you, maybe we can run through to resolve some of the issues that you might be facing in one of the discussion classes. Okay, so that is how our journey going to be for next couple of lectures now. Okay, so let's begin. Now let me get the pointer right here. Okay, now let's move on. Okay, so see, for a microcontroller, you need to be having this skill to look at the microcontroller architecture and understand some of the details of the architecture. Now there can be different levels of this architecture. Okay, I'll explain you what it means. So usually, there is a lot of information that will be given in terms of what this microcontroller can do and cannot do. These are given in terms of these kind of block diagrams, or some architectural understanding will be there. Okay, so we should have that ability to kind of get to see these block diagrams and figure out okay what it means for us. So we'll look at some of these kind of data sheets of the microcontroller, and then figure out. So this exercise we'll do as we go along, with the different microcontrollers and some of the things that we discussed in today's class also. So typically bit accuracy of processing these calculations. It is a 8-bit microcontroller or 16-bit or 32-bit kind of accuracy is there. Then what all interfaces are provided by this microcontroller. So if you start off with one of the base 8085 microcontroller, microprocessor actually, it was the basic computer chip to begin with, when Pentium chip came 586 kind of a thing, it is, you can go back in history and see it's 8085 was one of the first computers that was developed, and it's still good academic kind of understanding purpose. It is good to kind of see okay how that microcontroller really works. Okay, so some of the basic understanding of how the commands are executed in microprocessor or computer or microcontroller. There are similar kind of a ways the commands are executed. Okay, so that all we will see based on the the architecture and the block diagrams. Okay, so I'll post these data sheets of 8085 then some modern kind of microcontrollers and our ARM Cortex. Okay, so you can kind of compare these data sheets and see and kind of try to make sense of some of the things. Some part of the thing that is there, we'll try to go through some of the important aspects that we look for. So for example, these interfaces, in terms of interfaces, the 8085 will not have any interfaces to be provided. It will have just some kind of a ports that will be available as parallel ports or serial ports and things like that. And then one has to have some additional peripheral chips interfaced with this microprocessor to kind of make it microcontroller. So that is a basic difference to make it like a hardware interface for exchange of the data, not really microcontroller. Okay, so there is a difference between the word used as a microprocessor and word used as a microcontroller. So when you have a microprocessor, your Pentium chips and other kind of a computer chips are all your microprocessors actually, and they typically will have to be interfaced with the external peripheral chips to talk to any hardware or environment, or pinouts and things like that. But microcontroller will have all those peripheral also will be a part of the chip. So microcontroller chip will be a very tiny kind of a chip in which everything is there. You have your ADC DAC interface, or you name it, whatever interfaces that microcontroller provides, that are all already there on the chip itself, and only the pinouts terminals are out actually. Okay, but microprocessor, you'll have only the processing part on the chip, and then all the control part, the interfaces, peripheral devices, peripheral interfaces basically, they will be a part of additional chips that are provided on board. Okay, so the board will form entire control unit, but the chip by itself cannot form entire control unit by itself. Okay, so that is a difference between a microprocessor and microcontroller, and you should be aware about that. Okay, so let's move ahead for this basic architecture of 8085 system. Typically it is given in this kind of a form. Okay, this is like a base level architecture at the elements which are there in the microcontroller. So typically you'll have this data bus indicated. This represents like a bidirectional data bus. Okay, in some places there's a unidirectional data bus. Okay, it's not bidirectional. So this arithmetic logic unit is small kind of a processing unit in which these register can transfer data through this data bus, and the data from output of the ALU can be transferred to this this other data bus. Okay, so these are typically given kind of block diagrams. One can read through this kind of a block diagrams. Okay, what are things this microcontroller has inside. So this is not a microcontroller, this is in this case it is 8085 microprocessor kind of a chip, and it has this typically internal register arrays will be there. Okay, so this 8 number indicates that it is 8-bit register B, C, D. Some names will be given to the register. Then typically it will have a stack pointer, program counter. These are kind of some of the standard registers will be there in every microprocessor or microcontroller, and of course there will be this timing and control unit. Okay, so this is a architecture block diagram with a basic level kind of a block diagram of 8085. Nowadays, a modern microcontrollers, you don't see this kind of block diagrams. They'll give a more next layer of the block diagrams, in the sense they may not give you all these registers. They'll kind of, I'll show you some of the block diagrams. I mean, you'll get clear more clarity based on that. Okay, so when you say this is address bus, typically this data bus, if you see this 8-bit data bus is there, then address bus, address buffer is there. Address bus is AD17 to AD15. Okay, or address AD15 is like a 16-bit address bus is there for example for 8085 system of architecture. but like these kind of detailed specifications may not be there in the modern data sheets for modern microcontrollers. Okay, we'll just see some of the things there. So see that there are no external interfaces you can see in this 8085. Okay, so that's why it is microprocessor and not microcontroller, as we saw in the definition. Okay, then like that you can read these all the things that I talked about on the last slide. Okay, there are many kind of things you can make sense about, and the instructions, when they are given for such a microcontroller, then they'll be given in terms of these registers. Okay, so say there is a move instruction. Okay, contents of say move BC. Okay, so contents of register like C are moved to register B. Like that, some kind of a commands will be given, and their explanation will be given. If you don't know the structure of this architecture, then you will not make sense of those commands. Okay, so if this diagram is not given and I'm just giving this explanation of this command move BC, it's very difficult to kind of see what is going to happen in the system. Okay, so these architectural diagrams are kind of quite important for many microcontroller systems. Typically there will be these registers which are like indicating some kind of operation done or not done. Okay, so this is called a flag register. Okay, flag is like something which you show when something is done or not done or something like that. Okay, so this flag register also has this kind of a sense of notion that okay, it has some kind of a bits which are made 0 or 1 depending upon the operation that happens. So for example, like 0 flag will be set when some result of operation is 0. Okay, so this can be used for like further for looping operations. Say for example, if you have a variable which is decremented and like when it become 0, this flag is automatically set, and then like one can read the flag register and like take the control of the loop. Like okay, I need to exit this loop after that flag 0 happens there. So that is like a base level. That is what happens in the microcontroller or microprocessor. Okay, so this flag register is used for many of these control commands that you typically see, if while loops. Okay, so those kind of like breaking or like looping or like coming out of the loop or conditional kind of operation execution, that all depend upon this kind of a flag register. So flag register plays a very important role in any microcontroller. It will have it. I mean, you may not be able to see as a part of the architecture. It may not show that in modern microcontroller diagrams, but it is anyway there. So like that, there are many different kind of things that you can read through and make sense of. Okay, oh, this is what happens like that. Okay, so see, there is some other notes will be given, like operation outside ALU. Okay, such as this move command. Okay, move the contents of one register to other register. That will not affect the flag. Like that, something will be given. Okay, so each command, okay, reference or whatever this instruction set, it is called commands, or like commands of microcontroller are typically called instruction sets. Okay, these instruction sets give you the details of like what that instruction does in the microcontroller. And typically while giving that details, they'll refer to like say okay, the flag register is set, some bit in the flag register is set or reset, or like nothing is changed. Something like that will be given as part of the command instruction details. Okay. Now let's come to a little more modern microcontroller. If you see the data sheet, I'll share with you the data sheet. Okay, so this if you see, it will be like lot more complex microcontroller as compared to 8085. There are several, I mean many different registers. In fact, for each of the interface, you will have a different kind of a architecture block diagrams. Okay, so we as a user need not know like functionality of each of the registers. We are not interested in that. What we need to understand is okay, how these things are, and from programming perspective, how I can make use of this information that is given as a part of the architecture. Okay, that is what we are concerned with. We are not really interested in, like, how this microcontroller is designed or how it is working inside. No, we are not interested in knowing how it is working inside. Okay, although, I mean, as a curiosity, we may go into, like, a little bit more details of some of the things, but I mean, really, it is not needed to know what, I mean, or how things are working like that. So something is given, like, okay, if you adjust the contents of this register to this value, then this will happen, like that it will be given. So you just believe that it will happen. You don't need to kind of, like, know how it happens exactly. Okay, there are a lot more details about the architecture up to the register level needs to be known to kind of really figure that out. Okay, so we are not again going to get into those details, and, like, that is not the intention of this class. Okay, so our intention is to kind of, like, see these block diagrams and figure out, okay, how can I program this to kind of achieve what I want to achieve with this microcontroller. Okay, so that is what we are, like, looking at all these diagrams from that perspective, and generally to know what are the limits that this microcontroller can be stretched to. Okay, knowing the block diagrams, one can say, okay, oh, this cannot be possible with this microcontroller. Okay, this is absolutely, like, given the block diagram, reading the block diagram, you can come to that conclusion, okay, this particular thing cannot be possible, or this is up to this extent it can be possible. Okay, those kind of conclusions can be drawn very easily by looking at these architectural block diagrams and some of the data sheets of this. And in XCP 100, for example, there are several interfaces and modules for enhanced functionality. Like, you have digital IOs, then PWMs, then periodic interrupt timers, ADCs. Okay, these are, like, now kind of for a lot of modern microcontrollers. This will be definitely there kind of interfaces. Okay, the digital IOs will be definitely there. PWMs will be definitely there. So what we are talking about is now, like, this series of microcontrollers which are in the class of used as some kind of a mechatronics application. Okay, there is another class of these microcontrollers or microprocessors which are used for mobile platforms. Okay, so mobile or display applications. So there are many different series of or families of microprocessors the companies would have developed catering to different kind of needs of application. Okay, so these are so XCP 100, for example, has been designed for automobile kind of a controlling applications. Okay, so it will have the interfaces and other kind of these modules which are, like, specifically needed for those kind of applications. Okay, motion control applications. Okay, so those we will look at some of the microcontrollers or architectures of only those where, like, we have need for this motion control or mechatronics kind of application. Okay, so this is how, like, these microcontrollers will be there. And now, see, if you see at 8085, like, these commands here are going to be of this kind, like, what we saw, this move command, for example, to move these contents of this register. They are, like, basic assembly language kind of programs. Okay, so for example, here, like, we have this move command that we mentioned here. So they are, like, these are more like assembly language kind of a programs. So like, the microcontrollers like XCP, you don't kind of, like, start writing those assembly level commands to do the programming. What you do is, like, you do this programming in C rather than at the assembly level, and compiler, okay, typically, like, there will be an the environment will be there, development environment, integrated development environment. Okay, so that environment in this XCP, for a case, we have this code warrior kind of a software environment which will compile this C code and convert it into the assembly language, and actually carry out the operation of, like, dumping this assembly language code into memory of microcontroller to execute. Okay, so these all things are now done at a much higher level. Okay, so a user doesn't need to know what are the opcodes or, like, these assembly language commands that are used for executing your program. You just need to write your program in as if you are writing in C, and then your job is done. So we'll get into programming aspects pretty soon. Just hold on for a while. But this is important to know. Because now the efficacy of what you are using in C program and what gets converted into assembly language lies with this code warrior or whatever code composer studio in Tiva case. And so that compiler, okay, is determining, okay, although whatever you have written in C, how faithfully it is getting converted into code that microcontroller can understand or execute very easily. Okay, why I'm saying that is because, see, in C or C++, there are same thing can be done many different ways. Okay, and not all of those ways would have been there in the compiler to compile and produce the output for the assembly level program. Okay, so it may not be get compiled and nicely depend upon compiler specifications. No, it may or may not get compiled, and it may not kind of pop out also major errors. But you'll wonder, okay, why I'm in C everything looks fine, but it's still why it is not executing. Okay, if that kind of a situation comes, it's probably time to change the logic that you are using in C to some simpler kind of a logic. If you are using some kind of a complex logic, you can change it to some simpler logic and try again and see. So many times there are no unique or straightforward answers to some of these things. Okay, why it appears that I'm doing everything right in C, but somehow it is not getting executed in microcontroller. That scenario is not really uncommon in microcontroller programming. We'll come to the programming aspects sometime soon. So this is this is a kind of a block diagram or architecture of this XCP100 microcontroller, and here there is a memory blocks that are written, so there's a flash memory, RAM, EEPROM. It's a lot of different kinds of memories are written. Then voltage regulator, there are some kind of a pin outs and pin ins. One can read through the datasheet clearly to get understand more things. But one can see there are these some registers here PTE. These are all seems input output registers here. Okay, so that can exchange the data in the digital format, okay, with the outside environment. Then on this side you'll have this some ATD. This is like a analog to digital converters. So some interface for analog to digital conversion. So like that you'll find. See, this is a PWM interface here, synchronous serial interfaces, scan interfaces. So these are kind of different kinds of interfaces. So this scan, for example, is control area network interface. This is like a serial communication protocol only, but only for short distance kind of a communication. So these are developed for specific application. For example, CAN interface is developed for the automobile kind of application. Okay, Germany, it comes from Germany. German automobile manufacturers, they introduced this for the first time, and it became some kind of a standard. The way you have the serial interface UART as standard now. Okay, like that you'll find a lot of these interfaces that are provided by this XCP100 kind of a microcontroller. Okay, so for example, if you want to say, okay, oh look, can I have say 20 kind of analog sensors interface with my microcontroller? How do you kind of answer this question? Think about this. Okay, so 20 sensors I want to which are producing analog output, I want to interface with this microcontroller. Is it possible? Okay, by looking at this diagram, you need to look at where you'll give this analog input. You'll give this analog input to the A to D converters here. Okay, so this is this is a 16 channel A to D conversion. Okay, so this 16-bit thing is there, and then there is a there is 16 channel another A to D converter is there. So these two are seems to be same, although they are given some terminology different here. You see the numbers here. 16 to 0 channels are there. There are only 16 channels in this microcontroller. Okay. So what are these and what are these? There will be some small difference between these two cases. So one has to kind of see in little more detail in their thing. But there are 0 to 16 channels are there for this analog to digital converter. So I cannot interface 20 sensors, so I cannot use this microcontroller. Those kind of conclusions one can kind of draw. Okay. So if you get in this kind of confusion, okay, oh no, these are seems like 32 channels. No, but then you need to look at little more details in the data sheet, and you'll get to know that okay, oh no, there are actually only 16 channels that can be programmed. Okay, like that one can see okay, there are only 8 motors that I can run maximum through this XCP100. Okay, so there are 8 PWM channels to kind of run my 8 motors. Like that one can kind of conclude some of the things based on the architectural block diagrams, and then one can go in more detailed block diagram of each of the interfaces, which I have not included here. I mean, to kind of understand okay how that particular interface works. So how what are the different registers that are controlling that interface outputs. Okay, so those kind of details will be given in that architectural diagram of each of the interfaces. And that is important to know from programming perspective. Okay, so when we talk about programming, we'll deal with this in little more details. Okay, so let's move on from here. So this is another kind of important aspect to consider, that the pins may have different functioning. Okay, so pin details should be given, which pin is connected to this pin number is connected to what its function will be given. Okay, so this pin diagram details will be given in detail of each of the microcontrollers. So XCP100 for example, so this is a pin VSS. Okay, so if you want to find out this this is a supply voltage, so there is no other function for this pin. Okay, but for some of the other pins, there are some functions, this PT5, okay, has some other functions here. Okay, so how these functions, so the pin functions can change. Okay, one can program and change the pin functions. Okay, so that is what is important concept here to know. Okay, pin is not kind of having a fixed function all the time. That is possibility in the new modern microcontrollers. See, older microcontrollers, if you go for, there will be no fixed pin functionality. Okay, so GPIO pin will just do only digital input output. There is no other kind of a function that that pin can do. But now these modern microcontrollers will have this possibility of pins having multiple functions, and depending upon the package, this is different kinds of packages. Okay, this low profile quad flat package, okay, or a QFP, that those packages are where this how this chip is packaged, and these pins terminals are coming out is what it says. So this LQFP 144 means it has 144 pins that are coming out of this thing. So this is 112 LQFP. So 112 pins are there from these numbers from here to here. We'll have 112 pins that are given by this kind of a package. Okay, so each of the package, some package may be missing some pinouts. So you need to see, okay, what is the intention for you to program, and then you can select appropriate kind of a package for the microcontroller. Okay. So this is about like little bit more about this XCP100. So see, we are not looking at like all the entire information of XCP100 and then moving on to next. It's impossible to do that. If you see the datasheet of XCP100, it will be like about 1,000-page datasheet. Okay, you cannot expect yourself to go through the entire datasheet and then then only you are qualified to go for higher level. No, that's not a way to understand microcontrollers. It will take humongous amount of time, and then even then you will not be sure whether we'll be able to be skilled enough to do what we want to do out of that microcontroller. So this strategy or philosophy of using this information is what we need to understand here. Okay, so see, that's why we want this your background in the microcontroller domain. Any microcontroller domain is okay. I didn't say that okay, you should have the syntax of some microcontroller node. No, that is not requirement for this basic requirement for this course, because this philosophy of how do you kind of look for what in the is what is important, and that will come based on your some small experience that you had before in MATLAB, or your own kind of a microcontroller programming experience. Okay, so that experience is valuable because it gives you some kind of a philosophical understanding of things. Okay, so when you are now switching to new microcontroller, you know what to look for, okay, or what not to look for. Okay, both ways, so that is where your experience would be valuable here. And we understand some part, and then we say okay, oh, this part is not understood completely, but if we need that for something, we'll kind of get into more depth of that and come back to that. Like that we should understand. So if you are able to kind of understand these architectural diagrams well, a lot of things will be immediately very clear. Okay, so you can practice to go through some of these kind of diagrams of XCP100. I'll post these data sheets there, or your 8085 of course is very simple, but XCP100, some of the block diagrams you can go through and understand. Okay, oh look, I need to set some registers to get some meaningful operation done out of this microcontroller, and this all this what commands I should look for. I can look at these register details of this microcontroller block diagrams, and from there I can figure that out. Okay, so you don't start reading the datasheet as if you are reading a book. No, the way to read datasheet is okay, what is your intention, what do you want to do. Okay, I say okay, oh, my intention is to just program some digital output or input outputs. So from that perspective, I'll look at only that interface, which is digital input output interface for this microcontroller. Okay, so so that is how you look for appropriate things in the appropriate microcontroller datasheet. Okay, and then some names that will be given for these interfaces also will be different. So digital IO input output interface I say, but if you see in TIVA board, it is given as general purpose input outputs. Okay, GPIO kind of terminology that is used. In XCP100, I think there is some different terminology that I have used. Port integration module or something like that is given, PIT or something like that. Okay, so those names also will be different. Okay, so you need to look for those names, look for your digital input outputs, and then appropriately look for that particular interface, and then you go into that detail. So you should be open in some way to see that okay, oh, this digital input output is I'm searching for, but it is not there in this, or this kind of a thing may happen. I see the entire content, there is nothing written as digital input output, and there is nothing written as GPIO in one of microcontroller datasheet. Impossible. Okay, microcontroller should have some kind of a digital input output interface. So then its name you need to look at, that might have been different. Okay, so this is how, like, some things may differ from one family to other family, and we need to hook on to the philosophy very firmly. That philosophy is mostly same in one, like, multiple, across multiple platforms, and look for things that we want to do. Okay, so we'll have this opportunity to kind of, like, you already have some whatever microcontroller you have gone before through, but we'll have this opportunity to go through, like, little more details and actually program this ARM controller, Cortex kind of a series, M4 series controller.